Let me start. Thank you so much for coming. And as you all know, my name is Mojgan, and I'm assistant professor at forestry department. I have a 0 appointment at chemical engineering department at MSU, and I have a professor status only at the mechanical and industrial engineering department at University of Toronto. I'm going to talk about lignin, and to tell you what is lignin. Lignin is basically natural glue in the wood. Currently, pulp and paper industry, when they want to make pulp and papers, they basically start with a tree. They use the timber or to chips, make the wood chips, and they get a bark, debark the numbers, and then burn it as a steam. They use the chips to make use the cellulose part and make pulp and papers, and lignin and hemicelluloses, which are other main components of the woody plants or other plants, they basically burn them to make steams for the paper making machines. But in future, we are hoping that most pulp and paper industry stop doing that, because there is so much value added products that we can make from the bark, from the hemicelluloses to make biofuels and bioethanol and polymers, and also from lignin. And this is the part that I'm going to focus today, using lignin that is now produced as a byproduct of pulp and paper industry or bioethanol industry to make value-added products. And for the biorefinery, let me just clarify. When I'm talking about biorefinery, I mean lignocellulosic biorefinery, because currently there are biorefinery industry that they use corn to make bioethanol, but we are talking about like agricultural residue or lignocellulosic material to make bioethanol. Looking at the lignin, not only the amount of lignin varies based on the type of plants that we are talking, like for example, hardwood has less lignin than softwood, and annual crops or agricultural residue even have less lignin than hardwood. But the structure of lignin, depending on what type of oxidation process they use, is going to change. The amount and the chemical and physical and thermal properties of lignin is going to change based on the source and based on the extraction process that they use. Majority of the pulp and paper industry currently are using either kraft or organosol process. Oh, sorry, kraft or sulfite process. So the organosol and enzymatic hydrolysis is usually used for biorefinery application. And as you can see, yes. I can see them. Okay, I should stand here. Okay, thanks. Thanks for mentioning that. I don't know if they can see that the small thumbnail that I'm talking. You can see that? Okay, if I stand here, okay, sure. I'm gonna try to stand still. Okay, if you look at this, these are different lignin samples that we got from different isolation processes and different biomass sources. They come in different colors, some of them light beige color up to completely dark black, ranging from like a lighter brownish color to darker brownish, different particle size and completely different properties. If you're going to use lignin for bioproducts application, there are some challenges. One of the main ones that we are dealing, especially if you are using the lignin that is isolated from pulp and paper industry, is impurity, because they're using sulfite compound to isolate or dissolve lignin to have pure cellulose or high quality fiber. We're going to have lignin that they have high sulfur content and other impurities. The other challenge is non-uniformity of lignin, because it's a natural polymer. We have lack of consistency and high molecular weight distribution. I'm not going to get into technical details, but please feel free to write down your questions, or I'll be happy to answer them. Lack of functionalities, like even though we see different functional group in lignin, not all of them are available for reaction with the co-monomers. And that's another challenge that limits application of lignin in different polymeric industries. The dark color of lignin, as you saw, like if you're going to use like a dark brown or black color lignin, for instance, in paint that is white, it's going to be a challenge. We have to consider an application that the dark color of lignin would not be an issue. And that's, I'm going to explain throughout my talk too. Most lignin, we are okay, but if you have work field lignin, you probably have experienced that the craft softwood, especially the ones that they have high sulfur content, have a really unpleasant smell, but not the other type of lignins. There are tons of research going on by pulp and paper industry and other researchers trying to solve the unpleasant smell of the craft softwood during the isolation process. I'm going to talk about three main different categories of the products that we work in my lab. We use lignin to replace petroleum-based phenol for phenolic resin application that's currently used for making plywood and oriented strand board, OSB. We use lignin to replace petroleum-based polyol to make polyurethanes for coatings application, paint or coatings, for adhesives application or glue application or foams application. I'm going to get into much more details. And then we also use lignin to replace petroleum-based bisphenol A, which is a very toxic chemical in epoxy resin application. The lignin-based phenolic adhesives, I'm going to start with that. That was our first project. If you look at the structure of phenol formaldehyde adhesive that currently is used for plywood or OSB manufacturing line widely in the world, they have phenol and formaldehyde. The phenol, both of them are from petrochemicals. Formaldehyde has higher toxicity, but phenol structure is toxic if you are exposed in long term to phenol structures. Many industries who are thinking about sustainability and having a product that is environmentally friendly, they've been working the last 30 years to try find a substitute for lignin, for phenol. And if you look at the structure of lignin on the other side, you can see that even though it's complex, this is a very small section of lignin. It's much more complex than this structure that you are seeing. It has many phenolic structures, similar to phenolic structures. That's why we call lignin a natural polyphenolic compound, a good candidate to replace phenol in adhesives. What we did in our first study, we used the lignin that was isolated from corn stover. That then when I say corn stover, means corn stalk, corn cobs, and the leaves. Like what is the residual, not the corn itself. A company called Poet, they had a lignocellulosic biorefinery in Liberty plant that they were using the corn stover to make lignocellulosic bioethanol, and they have a leftover lignin. We use that lignin, and then that lignin has a very good structure with high phenolic content. Replace 100% of the petroleum-based phenol with this lignin, and then basically made the adhesives that was good for plywood application. That was the first time that we basically were able to use a lignin to replace 100% of the petroleum-based phenol with lignin without any modification. All the other studies that they've done it, they were able to replace up to 50%, not 100%. But this lignin had really good reactivity, and we were successful. And then recently, I have a project that is funded by CRIBE Association in Canada. This is a part of the consortium that I'm going to explain later. Mohsen, one of my PhD students, he used craft softwood and replaced 100% of the phenol with this lignin and formulated the adhesive that you see how nicely performed with high, dry, and wet adhesion strengths with 100% wood failure. Means that adhesives works really well. And this is again for the first time that has been done. And that's why when I applied for this grant from Center for Research and Innovation in Bioeconomy, is a Canadian institute that they were interested in scaling up production of lignin, like making value-added products with lignin. I have two lignin producers, Fortum from Finland and West Fraser from Canada, and Hexion, which is the major producer of phenolic resin in the world. They are interested in our technology. We're going to work with them that they can scale up our developed technology to make lignin-based adhesives, and we're going to try it on the manufacturing line of plywood in Rosebeck by 2023. But we didn't stop there, because even though we replace phenol with lignin, but formaldehyde is still toxic. And we were thinking about, we need to find another bio-based compound, less toxic compound to replace formaldehyde. Like almost 3 years ago, when I was talking with the R&D manager of one of the major resin producers, I told them, like he said, okay, you replace phenol with lignin, what's your next step? I said, my plan would be to replace 100% of the formaldehyde with glycol. He said, you can't do it. I said, why not? He said, because both of them are going to be less reactive. Formaldehyde is great. You can't do anything about formaldehyde. 2 years later, I told him, like, give me 5 years. And 2 years later, we were able to do that and now file for patent. And with this way, now we have a lignin-based formaldehyde free, which is very toxic. If you have like a plywood or a in your house, you're always concerned about formaldehyde emission. Now with this one, you don't have to be worried about formaldehyde emission. We have lignin-based formaldehyde free adhesives that this paper is ready for submissions that I plan to submit it tonight, actually. Should I stop and wait for questions, or should I continue? I think you can make a call. Should I wait for the end for the questions? Whatever you feel. Okay. Just make sure to write down your questions, because I'm moving to the next step. Now I'm going to talk about lignin-based polyurethanes. When I'm talking about polyurethanes, if you have hardwood flooring, if you have furniture, there's a chance that the varnish on the top of your wooden hardwood or furniture is a polyurethane coating. Or if you're working in a stadium, the coatings on the flooring is probably polyurethane, because it's highly chemical resistance and very high end coatings. The adhesives or glue, we're going to talk about coatings and foam. When we are looking at the structure of lignin, you see this is a very complex structure. This is the lignin from soft section. In polyurethanes, we have two main components, isocyanate and polyol. Polyol is a compound that has more than one hydroxyl group, OH group, and that's why they make the urethane linkages. But if you look at the structure of lignin, we have so many aliphatic hydroxyl groups, and we also have so many aromatic hydroxyl groups. Basically, lignin is a natural polyol, and that's why we target that to find out how we can make lignin-based polyurethanes. Mona, one of my PhD students, was sitting here. She actually measured the reactivity of 20 different lignin samples from different sources, different isolation processes with phenyl isocyanate and with the diisocyanate too. That's a fundamental study that helps us to understand how lignin reacts with different isocyanate that we have, with phenyl isocyanate, with diisocyanate. And then we try to use those information to make lignin for adhesives application, coatings, rigid foam, and flexible foam. With the adhesives application, we were able to replace 100% of the petroleum-based polyol with lignin, and then make a high solid, zero VOC, zero volatile organic compound, and an adhesive that contains more than 50% lignin on weight basis. There is no lignin modification. We just use lignin the way that it is. And this is a project that Said worked on that. And then we could cure this adhesive at room temperature, meaning minimum amount of energy required to cure, and we can cure it at higher temperature in shorter time. Currently, if you've been to the STEM building that is built of CLT, the CLT and glulam or mass timber are produced by polyurethanes adhesives. This is a very expensive adhesive. It's basically around $5 per pound, the commercial adhesives. And the orange bar that you are seeing, that's the commercial adhesives, and the green or lignin-based adhesives, cured at the same room temperature, same conditions, performing much better than commercial adhesives, and almost 5 times cheaper. We're going to do a cost analysis, and performs really good when we are using for adhesives. And that's why, through the same consortium that I built, I had 2 lignin producers, but this time, instead of Hexion, Henkel, which is the major polyurethane producer adhesives in the world, and majority of the CLT producers are buying their adhesives from Henkel. They're interested in scaling our technology. We're gonna, and then once they scale up our technology, make lignin-based polyurethanes adhesives, then we're gonna use it and try it in the manufacturing line of Element 5 in Canada, which is a CLT producer. The other projects that we work and recently filed for patents is what funded by DOE. The goal was to make polyurethanes but waterborne adhesive. This is coatings. This is the first time that any formulation with lignin is used for water-based formulation. Usually it's solvent-based because lignin is not soluble in water. Most lignins are not soluble in water. Lignin sulfonate is, but it's not suitable for this application. We were able to replace 100% of the petroleum-based polyol with lignin 80% and with 20% soy polyol to make it much more flexible. Most of them are bio-based. We use a bio-based solvent, silane, which is also produced from biomass. And then we also use tartaric acid, another bio-based emulsifier, which is basically the fruits like citrus and bananas, and they have tartaric acid. Entirely bio-based formulation, only using petroleum-based isocyanate in this case. We formulated and these coatings, and DOE was very happy with this result. When we applied the resin, the last one is a commercial PUD because it's colorless. On wood, you hardly can see the color change, but on metal, we can see the color change between the commercial polyurethane dispersion and other coatings. But for many applications, for example, inside the can coatings or many other applications, industrial coatings, they don't really care about the color. Therefore, lignin would be a good candidate for those kind of applications. Now moving on to the foams. I had a couple of different projects on flexible foam and rigid foam application. Why we are considering using lignin in foam application, not only improving sustainability, using renewable material, also if you have lignins, the flame retardancy, mechanical performance, lignin has antimicrobial resistance, antioxidant properties, and is biodegradable. All of this, imagine that if you have only, there was one study that showed if they add 2% lignin to the foam takes much longer to spread the fire. If we replace a certain percentage of the foam with lignin, and even delaying the fire for 15 minutes, that's a significant amount of time to give the residents to leave the building. That's why many industries are interested in using lignin because it's a natural flame retardant. And then when we are talking about foam, we have lignin, we mix it with polyol, catalyst, and then water as a blowing agent and mix it with isocyanate, and the foam, as we are mixing, the foam starts rising. Depending on the formulation, we're gonna have either rigid foam or flexible foam. The main difference, to simplify the difference between rigid foam and flexible foam. In rigid foam, 30% of the foam is petroleum-based polyol. That's the part that we're gonna replace with lignin. In flexible foam, 70% is polyol. And now you see the challenge. Why? Then later I'm explaining why we cannot replace 100% of the petroleum-based polyol in flexible foam with lignin, because lignin is aromatic and rigid. In rigid foam, the cells are closed because we want to get highest insulation properties. In flexible foam, the cells are open because we want that cushioning effect. And I'm just going to pass along some of these samples. As you can see, these are the light ones are the petroleum-based foams, and the dark ones are lignin-based foams. As you can see, for application, we can use rigid foam for insulation application in houses, or for a spray insulation, or for a structural insulated panel as a foam layer between the two OSB panels. For flexible foam, we can use it in automotive application, for furniture, for under carpet bedding, for cushioning, for footwear, all of those applications of flexible foam. This is a project that Christian worked, one of my PhD students. She's not here today because she's attending the Polyurethanes conference in Colorado now. She was able to replace between 0 to 100% of the petroleum-based polyurethane with lignin. And again, this is the first time that it's happening. There were some publications that they modified lignin, break down lignin to a smaller chain, or did oxypropylation. That is not like they use chemicals, toxic materials to do that, but this is unmodified solid lignin up to 100% petroleum-based, which is 30% of the total weight of foam with lignin, and that's again used for insulation application. In rigid foam application, we started with a project that was funded by Ford Motor Company in collaboration with Michigan Tech. Akash, one of my master's students that graduated last year, he was working on this project. We started by the control foam. We tested 16 different lignin and replaced 20% of the petroleum-based polyol with solid lignin. As you can see, like for example, the lignin that we had from bagasse lignin was light brown color, and the peanut shell lignin is actually gray. The others, Kraft softwoods and others, are ranging in different brown color. As you can see, when I'm talking about rigid flexible foam application, you see the cells are open. There is a hole fitting. That's the main aspect that we need for cushioning purposes of the flexible foam. Ford was very interested on this project, and what we end up happening, we found that when we are replacing 20% of the polyol with lignin, we're not only making that more sustainable, increasing the bio-based carbon content of these foams that can be used for automotive application, that we're gonna have, we improve the tensile, compression, tear propagation, and other properties of the foam, in addition to that flame retardancy, antimicrobial, antibacterial that I mentioned, lignin is there. Since Ford was really interested on this project, there was another call from CRIBE, and this time it was much more easier to form this consortium because they knew about our work prior to that. I have now 3 lignin producers: West Fraser, Fortum, and Sweetwater. Sweetwater is in New Jersey, Fortum in Finland, West Fraser in Canada, British Columbia. And we have 1 foam producer, Woodbridge Foam, which is in Ontario, Canada, but they have like basically branch everywhere that is on the world. And 1 automotive producer, Ford, because they saw the previous results. They all joined together. I submitted a proposal to CRIBE, and it's for $500,000, 18 months project. And then the plan is the Woodbridge Foam is going to scale up our technology, lignin polyol technology, to use lignin to make foam products in automotive. If you, I don't probably didn't mention, in every car there's 60 polyurethanes parts, like almost 30 kilogram of the weight of each car is foam. And increasing this bio-based content, even by 20% lignin, is a significant improvement for Ford. Ford is one of the leading automotive industry who have used soy polyol because of that bio-based content of the soy. And now through this project, another project that I have, we're going to mix lignin and soy polyol together to further increase the bio-based carbon content. And they're very much interested on that. The other category of the projects that I work, and the last one, is lignin-based epoxy resin. When I'm talking about epoxy, we basically have 3 main components, but the first 2 that we need to epoxidize is bisphenol A and epichlorohydrin. Bisphenol A is, if you remember, BPA free. If you see bottles for the kids, babies, that they say BPA free, like basically banned for some application because it's extremely toxic. But still, if you are using epoxy glue, epoxy coatings, epoxy adhesives, all of them still have this toxic bisphenol A. Our goal was that this company, Advanced Biochemical in Thailand, they are a branch of Asahi Glass in Japan. They approached me in 2017. And then I started talking to them. They said, we have a bio-based ECH, epichlorohydrin. We are interested to see if you can replace BPA with lignin and find which lignin or tanning is good for this application. I told them this is going to be a prototype study. I'm not going to promise 100% replacement. We're going to test the different reactivity and see whether it's working or not. And then 18 months later, we were able to replace 100% of the BPA with 16 different lignin and found the best one. And then use the bio-based ECH, which is made of glycerol, and made epoxidized lignin, and also use a bio-based curing agent, which is this one, cardolite, is from cashew nut shell, to make 100% bio-based epoxy resin. Nejad is now working on this project to use this bio-based epoxy resin and mix it with bamboo fiber to make composite products for automotive application. I have a meeting actually with this company and another company that they are interested that we form another consortium and scale of our lignin-based epoxy resin for different applications. And this is the list of current funded projects that I have. The first one that I mentioned is CRIBE on the wood bridge foams that my proposal got ranked as the first. I'm still waiting on the formal agreement that they tell me that I got the funding, but when it ranks first, you're almost 100% sure that they're gonna fund it. And then the second one, I got a grant from University of Michigan, M-Track programs, because we have a patent on that technology. They're interested that we scale up our lignin polyol and use it for flexible foam. Another funded project is by United Soybean Board that I got, and we are mixing lignin and soy-based polyol. The first one, M-Track projects, Kevin is working, my new master students, and the second one, lignin soy polyol, Enoch. Again, my new master students are working on these two projects. The fourth one is the CRIBE, the consortium that I mentioned. The phenolic part, Mojgan is working on that section, and then the polyurethanes part, Said, my PhD students, is working on that one. Then we have a DOE funded project to use lignin for proteins application that I mentioned is the main PI is Professor Eric Heck at MSU, and Said working on that project. DOE BIPs for the rigid foam is the PI is Dr. Marquis from Clemson University, and Christian is working on that project. The Ford Motor Company's project, Akash was working on that, and that project is going to end this December. And then the Formaldehyde Free USDA funding with Professor David Hodge in Montana State University. Mohsen is working on that project. And then durability of wood products, Composite Center. Nejad is working on that project, is funded by Wood-Based Composite Center. Another project that measuring lignin suitability for different resin, Mona, Said, and Mohsen are working on that project. Of course, these are the funding we got from different DOE, USDA, CRIBE, and WBC, and all the other producers. I'm very grateful for their support. Without them, there was no way that we could hire the graduate students and do this work. And more importantly, thank you to my graduate students. As you know, all thanks, everything that I've done, it wouldn't be possible without the graduate students. These are my group pictures before COVID. And then I basically put a picture of new students that joined after that, and with other students that I didn't have their pictures. Thank you so much to all of them for doing a fantastic job. And then I really appreciate your attention. If you have any questions, I'll be happy to answer. Sorry, should I stop the recording and sharing? Sure. Okay. If you have any questions, yes, Matthew? Thank you for a great presentation. Thanks. Yeah. Thank you so much for questions. I'm going to repeat the questions because of the audience that they're through Zoom. The question was that if you use lignin, whether it's going to be recyclable or biodegradable compared to petroleum-based polyol, and that's an excellent question. I'm actually collaborating with a professor in packaging department, Professor Rafael Ayuras. We are making foams. Actually, Kevin and Enak are making these foams downstairs because he's going to start this biodegradability test next week. We're going to test the petroleum-based foam and lignin-based foams for 2 different couple of months and monitors how fast they are degrading. Our hope is that because we are not modifying lignin, and lignin is biodegradable because if you put wood in the soil, it's going to degrade even in less than a year, depending on the condition. We are hoping that portion of the lignin in the foam is going to degrade and basically help with the recycling or resizing the foam. That's the hope. But I will have a much better answer in a year after we finish that study. Thanks. That's again very good question. Yes, please. Mm-hmm. 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 Yeah, that's again a very, very good question. The question was that how the lignin that you are using, not only from the biomass, the hardwood, softwood, or how it's going to be different from sapwood to hardwood or other parts of the tree, like young tree or old tree. That's again a very good question that I'm getting all the time from industry, because lignin is a natural polyo. There is a variation. And we know that the amount of lignin is going to be vary based on the, like, for example, the hardwood to the softwood or early wood, late wood. Like, for example, you have more lignin usually in late wood versus early wood because the cell wall are thicker. But what I propose to do, actually, I'm working with a company called Sweetwater, and through Wood-Based Composite Center, I submitted a proposal yesterday to a Wood-Based Composite Center because it's funded by Sweetwater. We are going to look at the lignin consistency. We know there is a significant variation between softwood, hardwood, or annual crops lignin or isolation process. But what we are going to study, we're going to study if they use the same biomass, for example, birch, and then use the same exact parameters, how variation in the biomass during the year at different times, like whether it's harvested in winter time, harvested in summertime, those variation, how is going to change the properties of the lignin. And I'm hoping again, in a year, we will have much better study to show that. We analyzed more than 80 lignin samples from all over the world, but from different sources and different isolation processes. But this is the first study that we're going to actually look at one source, one isolation process to see how it would change from time to time, from batch to batch. Excellent question. Yes. 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 Sorry, I'm going to repeat the question. The question was that when we were using lignin to replace phenol, did we also replace formaldehyde with another bio-based compound to have fully bio-based resin? And the answer is yes. The first project that we had, we only replaced 100% of the phenol with lignin. But the second project that we filed for patent, and Sasha and Mohsen was working on that project, we not only replaced 100% of the phenol with lignin, we replaced 100% of the formaldehyde with another bio-based dialdehyde, that is glycol. Glycol has still some toxicity, but significantly lower than formaldehyde. Like, there's no comparison between the two. But both of them are derived from bio-based, like biomass, basically, is a bio-derived compound. And this is not the formulation that Hexion is going to scale up, but they're going to scale up the lignin part. But now, because we showed that we can replace both of them at the same time, they're now interested to do the research on this one. Hopefully, they can scale up on both completely bio-based adhesives too. Thanks. I don't know whether I'm gonna get questions from the audience through Zoom. Should I check that chat? Okay, thanks for checking that. If you have any questions, people who are listening on the Zoom, please feel free either unmute. I don't think I can hear them. Please type your questions on the chat, please. Yes, please. There are, sorry, I also have to remind myself to repeat the questions. The question was that has any LCA analysis, life cycle analysis, has been done on lignin-based product? I've seen a couple of studies that they work on products that they were replacing only 30% of the petroleum base with lignin, but or less. But I'm actually working with a professor in North Dakota State University. She's in chemical engineering department, and she's expert on LCA and TEA. She's actually working with us to do the LCA of our lignin-based phenolic adhesives, working on that. And data seems very promising because of the lignin, but through the two CRIBE projects that I have, the consortium funding that I have, we're gonna work on LCA, TEA, and cost analysis. Work with the business school to do the complete cost and LCA, TEA, LCA, and cost and market analysis for those projects. I'm very hopeful we're gonna get very good results, but we never know until we do that. With the projects that I'm working with the DOE, with Professor Eric Heck, there is a person who does LCA and TEA analysis, but some portion of the lignin comes to us for polyurethanes application. They send another portion to University of Wisconsin that they are breaking lignin down to smaller molecules for chemicals. But the polyur portion is actually helps a lot with the TEA and LCA. But the complete LCA project is still ongoing. In a few months, we would see the complete LCA for that project that we use lignin for coatings application. Excellent point, and I can't wait to see those results. Any other questions? Yes. In market, the question was that how long it's going to take that we see lignin products in market. Lignin has been used in, for example, asphalt, for fertilizer, for animal bedding for a very, very long time. But this high-end application of polymeric resin that I'm talking, there are some adhesives, for example, that they basically replace 30 to 50%, in some cases even 70% of the petroleum-based phenol with lignin, but not polyurethanes. Polyurethanes hasn't been done. Epoxy hasn't been done. It's not commercial. Only the phenolic part, because people have been working on that for the last 30 years, but not 100%. Like usually when you develop a patent as a scientist, you end up like most of your patent end up sitting there and collecting dust after 30 years. I'm very excited and seeing that all these major resin producers are really interested in the scaling of that technology. That's a very, very like a good point, because if they are interested, they can make it happen. Like they know how to scale up. They know how to optimize the scale of pilot plant formulation. They know how to get it to market. They've been working on that. And one of the companies that I was talking with them last week, they said, Mojgan, we lost our hope in lignin, but you changed our mind. I was so happy to hear that. Like, see that they weren't able to work, but now knowing that what lignin to use, how the lignin chemistry works, what the resin chemistry is, choosing the right lignin for a specific chemistry, that's a key. And I'm really hopeful that Pale, Hexion, and Woodbridge Foam, and Huntsman and Dow, they are very interested in our technology, lignin polyurethane technology. We are signing the NDA with them. These companies can help us to scale up. But I think the best case scenario would be 5 years. I wouldn't say less than that, because it's going to take time. But the fact that they are started working with us, that's a good starting point, I guess. Yes. I'm not sure if I can hear them. If you don't mind, yeah. Yes, please. And then read the question.
So, Babak, if you're able to state your question through my computer, and I'll convey it to Mojgan.
Yes, sorry. I have a question from Dr. Nejad. Thank you for your presentation. I just wondering if your group considering using a continuous process like reactive extrusion for the modification or processing of lignin with other stuff or not?
Did you hear that?
No, not at all. Like, sorry, Bob, can you hear me? Can you please type your question if you don't mind in the chat?
Sorry?
It was very hard to hear.
Oh, sorry. I repeat my question.
Can you type your question?
Okay. Okay. I tried. Okay.
Thank you. Okay. Okay. Sure. See, typing. Consider reactive extrusion for the modification contract. The question is that whether we use reactive extrusion for modification or functionalization of lignin. No, we haven't. I know a couple of groups that they are working on that. Our goal in developing these products is basically using lignin without any modification, because there is tons of different publications that they modified lignin, and every single modification or functionalization is going to add to the cost. Extra step, extra chemical, extra energy. And since our goal was to use the bio-based compound, our main focus is to not only make these products more sustainable using the renewable material, but also follow the 12-step of principle of green chemistry, making sure that we are not using toxin solvent. We are developing a process that use similarly or less energy, using less toxic compound as much as possible, move away and make sure we don't do any functionalization and modification of lignin, and use lignin the way that it is. And I think that's the main reason that many of these industries are interested in our technology, because we don't have extra step and they can use lignin the way that it is. Just buy it from pulp and paper industry or buy it from bioethanol industry and use it directly in their technology. I hope I answered your question. You're welcome. Any other questions from the audience on the Zoom? I think for people on the Zoom, it would be great if you can type your questions. If not, I think I'm gonna type my email there. It was at the end of my presentation. I'm gonna type my email address, and then you can feel free to email me if you have any further question later on. It's just my last name, nejad@msu.edu. Any other questions? Okay. If not, should I stop the recording? Thanks.